I hope to conclude this first lecture with a statement of the fundamental theorem of asset pricing. And then I will hopefully next lecture give a proof of that result. I hope that this will be accessible to a lot of people without any advanced math background. You don't even need to have taken calculus really. Although some of the notation may be a little unfamiliar, and I will try to explain that along the way. My inspiration for this series is realizing how little background you need to develop some interesting ideas. So let's begin. We start with some finite sequence of times, 0 up to capital N, and we think of there being some process that's unfolding over this sequence of times. So for our purposes, the price of an asset, which you check in on at each of these times, or it could be more simply a coin flip process where you're going to flip a coin at each of these times. To keep track of what's going on with this process, we use a finite set omega. So omega is a finite set. And the elements of omega represent outcomes of this process. And by outcome, I don't just mean the value of the process at the last time step. What I mean is the entire history of the process over all of these time steps. So for instance, if we're doing a coin flip process, one of the elements of capital omega might be the outcome that all n+1 flips are tails. Another element of omega will be that all n+1 flips were heads, etc. So in all, we'll have 2 to the n. In that case, omega will have cardinality 2 to the n. Sorry, 2 to the n+1. And we also use omega to keep track of how much we know about the process at a particular point. So what do I mean by that? We use to capture that notion something called a partition. So a partition is just some collection of subsets of omega whose union is all of omega and such that they are also pairwise disjoint, meaning that they don't overlap at all. So this would be one partition of omega into 3 subsets. How does this represent our state of knowledge about the process? Well, the idea is that if this particular partition represents our state of knowledge, then we know which of these 3 subsets we are in, or which of these 3 subsets contains the ultimate outcome of the process. So let's think about our coin flip process, for instance. At time t equals 0, we know nothing about what the ultimate outcome of the coin flip process is going to be, so we represent that with sort of the indiscrete partition, where the only subset we have is the whole space. At time t equals 1, we flipped the coin once, and our space splits into 2 subsets. One that contains all of the outcomes where the first flip was heads, so heads, ... and then tails, ... Then of course at t equals 2, our space splits again into heads, ... heads, ... heads, tails, ... tails, heads, ... and tails, tails, ... and so on. And then at until time t equals capital N, at which point our partition has one subset for each element of the space capital omega. So it's somehow the maximal partition at time t equals capital N. It can't get any bigger, and so on. And how many, in this particular coin flip process, how many elements are there in this partition? How many subsets? Well, there's one for each element, so that means that there are 2 to the n. 2 to the n+1. Singleton subsets. Singleton just means a set that contains a single element. Okay, and this is this sequence of partitions that I've just talked about is an example of something called a filtration. So filtration is a sequence of partitions so F0, so one for each time step. So we assume throughout that we fix some particular set of time steps. F0, F1, F2 are the elements of the filtration up to capital N. Where, so notice that in this partition that I've given here, in this filtration that I've given here, each particular partition is somehow a refinement of the previous one. So I'll say, so where Fn plus 1 is a refinement of F sub n. So I'm not going to formally define refinement. I hope it's clear from the picture. So the idea is that for any piece of the partition at time t equals n, that piece is a subset of one of the pieces of the partition at the previous time step. Okay, so this is the notion of a filtration. And now I need to talk about how filtrations interact with functions, because we get our information about our process from a sequence of functions, as we'll see. So if x is some function from omega to a set E, and f is a partition of omega, we say that x is f measurable just in case x is constant on the pieces of the partition F. So here's the picture for that. We have our set omega. We have some partition of omega, omega 1, omega 2, omega 3, and we have our function x going to some set E. And we say that x is measurable with respect to this partition if it's constant on these pieces, meaning that if it takes a particular value at some omega in omega 2 and there's some omega prime also in omega 2, then it has to take the same value at those 2 points. So x of omega is equal to x of omega prime. So it has to take the same value on this whole set, and likewise for these other two sets. So in general, measurability requires a different definition, but in the case where omega is a finite set, and when say the singletons in E are measurable, then this is what it boils down to. So for our purposes, this will suffice. And you can see that if you know the value of x, then the value of x provides you no more information than the original partition provided to you, because remember that the information provided to you by the partition is to tell you which of the pieces that you're in, which of the pieces contains the outcome of your process. And if all you know is the value of x, then all you know is you know no more than which of these pieces you're in, because x is constant on the pieces. So now I can define a stochastic process. So a process is nothing more than a sequence of functions. x0, x1, up to x capital N, going from omega to some set E. And by the way, this set E in our cases will be almost always either R or some Euclidean space, meaning a product of the real line with itself a bunch of times. So this is what a process is. It's merely a sequence of functions that you can abbreviate x sub n. And if f sub n is a filtration, which recall means just a sequence of partitions where any one is a refinement of the previous one, is a filtration, and we say then x, this process, is fn adapted if each of these x n's is fn measurable. For n equals 0, 1 up to capital N. So now that I've said what a process is, I can define an asset. An asset we identify with its price process. Given some finite set omega and some filtration Fn, an asset is a positive real valued and Fn adapted process. So in our definition of a process, we had this codomain E. In this case, the codomain E is the positive real numbers. And then a market is simply some finite set of assets. S0 up to SD. Where here I omit the subscript n. Now we want something to model a particular strategy that you might have for buying and selling these assets in the market. So strategy phi sub n, and I'll write the components with the lowercase phi, phi 0 up to phi sub d, is a rd plus 1 valued predictable process. Where I haven't defined predictable yet, I will in a moment. So this strategy is going to represent, so the components of the strategy, these lowercase ph's are the components of the strategy, and they are each r valued. And each phi superscript I corresponds to s superscript I in the market, and it tells you how much of the asset Si you choose to buy at time n. In fact, at time n minus 1, as we'll see. So what does predictable mean? It means that each phi n is not Fn measurable, but Fn minus 1 measurable. Why do we require that? It's to model the fact that your decisions about which assets to buy and sell they sort of lag behind the events in the market. If price is updated and then you could somehow retroactively decide how much of that asset you owned before the price was updated, then it would be a very easy game. But in reality, it works the other way. So the particular positions that you take in the market, these phi sub n's, are decided upon, must be decided upon at time n minus 1. That's why they are n minus 1 measurable. And that is to say that they are made using only the information that the strategy has at time n minus 1. Then prices are updated from Sn minus 1 to Sn, and you calculate your gains and losses. So given this notion of a strategy, recall that phi n is just how much of the asset Si you own at time n. It's clear how the value of this strategy or portfolio, sometimes I'll use those two interchangeably, should be calculated at time n. So the value of a strategy phi at time n is just the sum from I equals 0 to d of how much you own of the ith asset times the price of the ith asset. And we denote this phi sub n of phi. And sometimes I will also write, actually quite often I will also write capital phi sub n dot s sub n for this sum here to represent the value of phi. So if you know what the dot product is from linear algebra, this is just dotting these two vectors. But it's important to remember that these are also functions on omega. Now, one further assumption we often make about our assets is that the first one, this S0, is a riskless asset. And formally, all this means for us is that at time n, it has value 1 plus r to the n for some r, some positive real number r that's constant, it doesn't depend on n. And we use this sort of riskless asset to somehow deflate the value of our portfolio. That is to somehow gauge its performance against the performance of sort of the trivial strategy of just holding treasury bonds and just taking a constant rate of return. So the discounted value of a strategy phi is merely the value of phi multiplied by 1 over the value of the riskless asset at time n. And we denote this phi n tilde of phi. And we won't need this notion until the very end of this first lecture when we state the theorem that we're building to. So now we come to a slightly more interesting definition that captures our notion that the strategy in taking a particular position in the market will only use the resources that it has available to it from making use of the assets that it already has in its portfolio. So this is the notion of a self-financing strategy. So a strategy is self-financing if for n equals 0 up to capital N minus 1, we have that the value of phi, which recall is phi n dot Sn, we say that it's self-financing if this is equal to phi n plus 1 dot Sn, where this expression here is phi n plus 1 I times Sn I summed from I equals 0 up to d. This thing on the right, this expression here, you can interpret as the cost to the person employing the strategy of taking the position phi n plus 1 at time n. Right? He takes this position, phi n plus 1, recall, at time n, using only information at time n. That's why phi n plus 1 is required to be Fn measurable. He takes that position when prices are therefore S sub n. So this thing on the right is actually the price to him, the cost of taking the position phi n plus 1 at time n. The thing on the left is the value of the portfolio at time n. So all this is saying is that the cost of taking the next position is equal to the value of the portfolio at that time. So there's no money coming in from outside, and the person employing the strategy is not consuming any of the portfolio. They're employing all of it to take the new position. So notice that if phi is self-financing, then we can write the difference in the value of the portfolio from n to n plus 1 as, so this is the value at time n plus 1 is phi n plus 1 dot Sn plus 1, and the value at time n is phi n dot Sn. So now, so far we've only rewritten the left-hand side, just using the definition of the value of the strategy. But now we'll use the self-financing condition. So the self-financing condition says that we can rewrite this second term as phi n plus 1 dot Sn, so that if we factor out the phi n plus 1, we'll get phi n plus 1 dot Sn plus 1 minus Sn, which should make sense because all we're saying is that if phi is self-financing, then the change in the value of the portfolio from one time step to the next is simply the new positions that you took in the market times the difference in the prices after they've updated, which is what we would expect. I want to, just for the sake of keeping our feet on the ground a little bit, to unpack all of this notation here, because it's a highly condensed notation. So this dot here, recall, means we're summing. So we're summing phi I n plus 1 and against Si n plus 1 minus Sin. But recall also that all of these things are functions on omega for fixed n. So I'm also going to write in omega here. I will usually not use this expanded notation, but I just, at least once, I want to emphasize all of the information contained in this notation. So at each time we get a sum, and that sum is a function on omega. I want to emphasize something that I'm not sure I mentioned, which is that our strategies, let's see, where did I define strategy? Here, is defined to be an RD plus 1 valued predictable process. So the components are real valued, in contrast to the definition of an asset, which required the process to be positive real valued. A strategy can have components that are negative valued because we want to capture the notion that you can borrow an asset. So that's what having a negative a coefficient for that asset would be interpreted to mean. Shorting the stock or borrowing some money from the bank or something like that. So self-financing is one condition that we might impose on a strategy. Another is that the strategy never goes bankrupt. In other words, its value never drops below zero. So phi is called admissible if its value is greater than or equal to 0 for all n, so for any from 0 up to capital N. What does this mean? Recall that Vn of phi is a function. So what does it mean to say that it's greater than or equal to 0? Well, it means that Vn phi of omega is greater than or equal to 0 for all omega in capital Omega. This little epsilon here means contained in, so little omega is an element of capital Omega. Oh, sorry, that's one condition for admissible, and then the other condition, and if phi is self-financing. So two conditions to be admissible. And now I can tell you what it means for a strategy to be an arbitrage strategy. Arbitrage basically means that you get something for nothing. And in this context, what it will mean is that you have a strategy that starts with 0 value, a self-financing strategy, in fact an admissible strategy that starts from 0 value, and it somehow terminates with non-zero value, positive value, for some omega. Say a strategy phi is an arbitrage if phi is admissible, meaning that it's self-financing and its value never drops below 0, and if the initial value of the strategy is 0 and the final value is not 0, meaning that for some omega it's strictly positive. So this is the case for some omega in capital Omega. So an arbitrage is a strategy that gives you the possibility, the strictly positive possibility, of something for nothing. This is something we generally want to exclude. So a market, which recall is the data of an omega and a filtration and a finite set of assets, is called viable if it does not admit an arbitrage strategy. So if there does not exist an arbitrage. And now I'm almost ready to state the theorem that we're building to, but I need a little bit more machinery coming from probability theory. So I'll now define, well, what for us will be a probability measure. It's a definition that works when your space is finite and when all of your singletons are measurable. So a probability measure on some finite set omega is a function, I'll call it capital P, from omega, and it's going to be strictly positive. It's going to take values between 0 and 1, but it's going to excluding 0. And it must have the property that when you sum all of these values, you get 1. So far we can talk about the probability of a particular omega, because P is defined on the set omega, but we also wanted to define it for subsets of omega. So if A is a subset of omega, we define P of A simply to be the sum of the values that P takes on the set A. So it's this sum. So this is what we think of as the probability of A, or you can think of it as, yes, the probability that some event in A occurs. Also, for a function x from omega to r, I want to define the expected value of x, or the integral of x, with respect to the probability measure p. And we can do that as follows. Define the expectation of x, or this is just more notation for that, the integral of x dp. So this is the expectation with respect to p, to be the sum of the values of x against the probability of the elements on which it takes those values. So the sum over all omega and capital Omega of x of omega times p of omega. So this is the expected value of some random variable, or in our language just a function from omega to r. And more generally, if A is some subset of omega, we define the expected value of x over A, or this is also written the integral of x over A dp, to be the sum of omega in A, x of omega times p of omega. Okay, and that's the integral of x over A, or the expected value of x over A, with respect to assuming p is our probability measure. Now I'm building toward the notion of a martingale, which is the last piece of conceptual machinery we need before we state the fundamental theorem of asset pricing. But before I tell you what a martingale is, I need to tell you what conditional expectation is. So if x from omega to r is a function, and if f is a partition of omega, we define a function that we denote in this way: expectation of x relative to f. Oh, and we also assume that there's a probability measure. So we have omega and we have probability measure on omega. So the conditional expectation of x relative to the particular partition is a particular function on omega, values in r, and it's defined in this way. We define this as follows. For omega, so for a particular element of capital Omega, if omega lies in a piece of the partition, so I'll call the piece omega 1, of the partition F. So the picture is that we have our omega, we have our partition, so maybe this is omega 1, omega 2, omega 3, and we have an omega that lies in omega 1, and we have our function x going to r. And how should we define? We need to define this function if we need to define its value on this element omega, then we define its value to be 1 divided by the probability measure of the probability of omega 1, the piece that omega lies in, times the integral of x dp over omega 1. So in rewatching the lecture, I realized that I forgot to include the argument here, omega. Of course, I'm defining this function at omega, so I should have written in that argument there. So please just mentally insert that. So the intuition here is that we define this conditional expectation function via some kind of averaging process. So we somehow average the values of x on the particular piece that omega lies in, but we average them, weighting them against their probabilities assigned to them by the probability measure. And that's what this p of omega 1 here in the denominator is doing. It's sort of the divisor that you get when you take an average. And in this way, we get a function, conditional expectation function, which somehow approximates x. It approximates that original function x, but it also happens to be measurable with respect to the partition. So notice that this function will be constant on all the pieces of the partition. So it's somehow the function which is measurable with respect to the partition that best approximates the original function. And it has two properties that I'll list that you can easily verify. One is, as I said, so these are properties. As I said, this function is measurable with respect to the partition. Is f measurable? That is, it's constant on the pieces of the partition. And the second property that you can verify is that if A is a union of pieces of the partition, then when you integrate x over A dp, you get the same thing as if you integrated the conditional expectation of x with respect to f dp. So this second thing you can easily verify. You might first verify it by checking the case where A is an actual element of the partition. So if A is omega 1, check that these two expressions agree. And then you'll see that if you take a union, so if you took omega 1 union omega 2 for your A, you'll also get equality here. Okay, so that's the conditional expectation function. And now finally I can tell you what a martingale is. So for a martingale, we assume that we have an omega finite set, some probability measure p, and we have some filtration, f sub n. So a process x sub n equals 0 to capital N is a Fn martingale just in case xn is adapted, is Fn adapted, meaning that each xn is Fn measurable. And the more interesting condition is the conditional expectation of xn with respect to the previous partition is equal to xn minus 1 for n equals 1 up to capital N. And the intuition here is that if you're at time n minus 1 and you're trying to guess the value of xn using the information that you have at time n minus 1, the expected value of xn given the information that you have at time n minus 1 is simply xn minus 1. So think about the value of think about a stock price process. So if stock prices are martingales, it would mean that given all of the information that I have today, the expected value of the stock price tomorrow is nothing more than the stock price today. And I think that you can see this is a somewhat natural condition to impose on something like the process of a stock price. And now finally I can state the fundamental theorem of asset pricing. And to state this, I need to recall this notion of a discounted price. But in fact, I forgot to define the discounted price of an asset, although you probably could have guessed what I mean by this, since from how I define the discounted value of the portfolio. So given this assumption that S0, the first asset in a market is a riskless asset that has this value, 1 plus r to the n for some fixed constant r greater than 0, then the discounted value of an asset Si is just Si tilde. So at a particular time, it's Si tilde sub n, which is just Si times the value of the riskless asset. In the same way that we deflated the value of the portfolio, we just deflate the price of the asset, each individual asset. So that's what's meant by discounted value of the assets in a market, just dividing by the value of the riskless asset. And so now, finally, I can actually state this theorem. So the fundamental theorem of asset pricing says that a market, which recall is the data of a finite set, a filtration, and some finite set of assets, where the first asset is a riskless asset. This market is viable, which recall means that it admits no arbitrage strategy, if and only if there exists some probability measure P on omega with respect to which the discounted prices are martingales. So this notion of being a martingale is relative to a particular probability measure. That's why I had to introduce all this probability theory in order to define the notion of a martingale. Okay, so that's the result that I was building to, and in the next lecture I will prove this result.